Hello friends, in few of the earlier lectures we have been working on one of the goals of physics, that is how an electric field can produce an electric force on a charged object. A similar and closely related goal is the study of how a magnetic field can produce a magnetic force on a moving charged particle or on a magnetic object such as a magnet. You may already have a hint of what a magnetic field is if you have ever attached a note to a refrigerator door with a small magnet or accidentally erased an audio or video cassette. The magnet acts on the door or cassette via its magnetic field. The applications of magnetic fields and magnetic forces are countless and changing rapidly every year. Although digital technology has largely replaced magnetic recording, the industry still depends on the magnets that control CD and DVD players and computer hard drives. Magnets also drive the speaker cones in headphones, TVs, computers, and telephones. Most security alarm systems, doorbells, and automatic door latches employ magnets. In short, you are surrounded by magnets. The science of magnetic fields is physics. The application of magnetic fields is engineering. Both the science and the application begins with the question, what produces a magnetic field? Because an electric field is produced by an electric charge, we might reasonably expect that a magnetic field is produced by a magnetic charge. Although individual magnetic charges called magnetic monopoles are predicted by certain theories, their existence has not been confirmed. How then are magnetic fields produced? There are two ways. One way is to use moving electrically charged particles such as a current in a wire to make an electromagnet. The current produces a magnetic field that can be used, for example, to control a computer hard drive or to sort scrap metal. The other way to produce a magnetic field is by means of elementary particles such as electrons, because these particles have an intrinsic magnetic field around them. That is, the magnetic field is a basic characteristic of each particle, just as mass and electric charge are basic characteristics. As we shall be discussing in later lectures, the magnetic fields of the electrons in certain materials add together to give a net magnetic field around the material. Such addition is the reason why a permanent magnet has a permanent magnetic field. In other materials, the magnetic fields of the electrons cancel out, giving no net magnetic field surrounding the material. Such cancellation is the reason you do not have a permanent field around your body. Our first motive in this lecture is to define the magnetic field. We do so by using the experimental fact that when a charged particle moves through a magnetic field, a magnetic force acts on the particle. Definition of magnetic field. We determined the electric field at a point by putting a test particle of charge q at rest at that point and measuring the electric force acting on the particle. We then defined electric field as electric force divided by charge of the test particle. If a magnetic monopole were available, we could define magnetic field in a similar way. Because such particles have not been found, we must define magnetic field in another way, that is, in terms of the magnetic force exerted on a moving electrically charged test particle. In principle, we do this by firing a charged particle through the point at which magnetic field is to be defined using various directions and speeds for the particle and determining the magnetic force that acts on the particle at that point. After many such trials, we would find that when the particle's velocity is along a particular axis through the point, the magnetic force is zero. For all other directions of particle's velocity, the magnitude of magnetic force is always proportional to V sin phi, where phi is the angle between the zero force axis and the direction of particle's velocity. Furthermore, the direction of magnetic force is always perpendicular to the direction of particle's velocity. We can then define a magnetic field to be a vector quantity that is directed along the zero force axis. We can next measure the magnitude of magnetic force when particle's velocity is directed perpendicular to that axis, and then define the magnitude of magnetic field in terms of the force magnitude as B is equal to Fb upon Qv. Here Q is the charge on the particle. We can summarize all these results with the following vector equation. Magnetic force vector is equal to charge on the particle multiplied by particle's velocity vector into magnetic field vector. That is, the force on the particle is equal to the charge times the cross product of its velocity and the field, all measured in the same reference frame. The magnitude of magnetic force is given by this equation as Fb is equal to Qv B sin phi. The equation also tells us that the magnitude of the force is zero if the particle's velocity and magnetic field are either parallel or antiparallel, and the force is at its maximum when the velocity and magnetic field are perpendicular to each other. Finding the directions. Figure shows two right-hand rules for determining the direction of the cross product of particle's velocity vector and magnetic field, that is V into B, and determining the direction of magnetic force. The rule in figure A depends on our right hand rule, where you point the four fingers of your right hand along the direction of particle's velocity vector with the palm facing magnetic field and curl them towards magnetic field. Your extended thumb, which is at a right angle to your fingers, points in the direction of cross product of particle's velocity vector and magnetic field. Because magnetic force is in the direction of your thumb if Q is positive and is opposite the direction of your thumb if Q is negative. An alternative rule is shown in figure B. Here the thumb points in the direction of particle's velocity vector and the extended fingers in the direction of magnetic field. Now the magnetic force on a positive charge extends outward from the palm. The advantage of this rule is that the force on the charge is in the direction you would push on something with your hand, that is outward from your palm. The force on a negative charge is in the opposite direction. You can use either of these two right hand rules. Magnetic field lines. We can represent magnetic fields with field lines as we did for electric fields. Similar rules apply. The direction of the tangent to a magnetic field line at any point gives the direction of the magnetic field at that point, and the spacing of the lines represents the magnitude of the magnetic field. The magnetic field is stronger where the lines are closer together and conversely. Figure shows how the magnetic field near a bar magnet, a permanent magnet in the shape of a bar, can be represented by magnetic field lines. The lines all pass through the magnet and they all form closed loops. even those that are not shown closed in the figure. The external magnetic effects of a bar magnet are strongest near its ends, where the field lines are most closely spaced. The closed field lines enter one end of a magnet and exit the other end. The end of a magnet from which the field lines emerge is called the north pole of the magnet. The other end, where field lines enter the magnet, is called the south pole. Because a magnet has two poles, it is said to be a magnetic dipole. Earth has a magnetic field that is produced in its cores by still unknown mechanisms. On Earth's surface, we can detect this magnetic field with a compass, which is essentially a slender bar magnet on low friction pivot. This bar magnet on this needle turns because its north pole end is attracted towards the Arctic region of Earth. Thus, the south pole of Earth's magnetic field must be located towards the Arctic. Logically, we then should call the pole there a south pole. However, because we call the direction north, we are trapped into the statement that Earth has a geometric north pole in that direction. With more careful measurement, we would find that in the northern hemisphere, the magnetic field lines of Earth generally point down into Earth and towards the Arctic. In the southern hemisphere, they generally point up out of Earth and away from Antarctic, that is, away from Earth's geomagnetic south pole. Crossed fields. Both an electric field and a magnetic field can produce a force on a charged particle. When the two fields are perpendicular to each other, they are said to be crossed fields. Here we shall examine what happens to charged particles, namely electrons, as they move through crossed fields. We use as our example the experiment that led to the discovery of electron in 1897 by J.J. Thomson. Figure shows a modern, simplified version of Thomson's experimental apparatus, a cathode ray tube which is like the picture tube in an old type television set. Charged particles are emitted by a hot filament at the rear of the evacuated tube and are accelerated by an applied potential difference V. After they pass through a slit in screen, they form a narrow beam. They then pass through a region of crossed electric and magnetic fields headed towards a fluorescent screen where they produce a spot of light. The forces on the charged particles in the crossed fields region can deflect them from the center of the screen. By controlling the magnitudes and directions of the field, Thomson could thus control where the spot of light appeared on the screen. Recall that the force on a negatively charged particle due to an electric field is directed opposite the field. Thus, for the arrangement, electrons are forced up the page by electric field and down the page by magnetic field. That is, the forces are in opposition. Thomson's procedure was equivalent to the following series of steps. Set E is equal to 0 and B is equal to 0 and note the position of the spot on screen S due to the undeflected beam. Turn on electric field and measure the resulting beam deflection. Maintaining electric field, now turn on magnetic field and adjust its value until the beam returns to the undeflected position. With the forces in opposition, they can be made to cancel. When the two fields are adjusted so that the two deflecting forces cancel, we have from equations A and C, QE is equal to QV into B sine 90, which is equal to QVB, or V is equal to E upon B. Thus, the crossed fields allow us to measure the speed of the charged particles passing through them. The Hall effect. As we just discussed, a beam of electrons in a vacuum can be deflected by a magnetic field. Can the drifting conduction electrons in a copper wire also be deflected by a magnetic field? This was proved by Edwin H. Hall that electrons in a copper wire can be deflected by a magnetic field. This effect is known as Hall effect, and it allows us to find out whether the charge carriers in a conductor are positively or negatively charged. Beyond that, we can measure the number of such carriers per unit volume of the conductor. Figure A shows a copper strip of width d carrying a current I whose conventional direction is from the top of the figure to the bottom. The charge carriers are electrons, and as we know, they drift in the opposite direction from bottom to top. At the instant shown in figure A, an external magnetic field pointing into the plane of the figure has just been turned on. From equation B, we see that a magnetic deflecting force will act on each drifting electron, pushing it towards the right edge of the strip. As the time goes on, electrons move to the right, mostly piling up on the right edge of the strip, leaving uncompensated positive charges in fixed positions at the left edge. The separation of positive charges on the left edge and negative charges on the right edge produces an electric field within the strip, pointing from left to right as shown in figure B. This field exerts an electric force on each electron, tending to push it to the left. Thus, this electric force on the electrons, which opposes the magnetic force on them, begins to build up. An equilibrium quickly develops in which the electric force on each electron has increased enough to match the magnetic force. When this happens, as in figure B, the force due to magnetic field and the force due to electric field are in balance. The drifting electrons then move along the strip towards the top of the page with no further collection of electrons on the right edge of the strip, and thus no further increase in the electric field. A Hall potential difference is associated with the electric field across strip of width d. The magnitude of the potential difference is V is equal to E into d. By connecting a voltmeter across the width, we can measure the potential difference between the two edges of the strip. Moreover, the voltmeter can tell us which edge is at a higher potential. For the situation of figure B, we would find that the left edge is at a higher potential, which is consistent with our assumption that the charge carriers are negatively charged. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. A magnetic field is defined in terms of the magnetic force acting on a test particle with charge q that moves through the magnetic field with a particular velocity and in a particular direction. The Hall effect states that when a conducting strip carrying a current is placed in a uniform magnetic field, some charge carriers build up on one side of the conductor, creating a potential difference V across the strip. The polarities of the sides indicate the sign of the charge carriers. So that is it for today. See you in the next lecture, where we shall be discussing magnetic force on current carrying wire. Thank you very much.